We're about to derive the special functions called the spherical harmonics. The Lie algebra for the orthogonal group in 3 dimensions, like the harmonic oscillator algebra, can be expressed in terms of the basic Heisenberg algebra, x, p, and I, which can serve to give a spatial representation to the Lie algebra itself. These structures arise from finding the functions y, eigenvalues, projected onto the Casimir operators, the d operators, and the h eigenvalues, which in the current case is an r, l, and m, where l and m are like j and m, for the orbital angular momenta and its z component, and the r, and where y1, y2, and y3 are the eigenvalues of x, y, and z. Equivalently, if we know x, y, and z, the eigenvalues of x, y, and z, which are y1, y2, and y3, then by going over to a spherical harmonic, we can re-express, rather than using those three components, we can re-express those into r, theta, and phi. We're going to project that onto another basis of a commuting set in which r commutes with the angular momentum, because r is a scalar under the angular momentum, so we can in fact diagonalize simultaneously not only L squared and LZ, but also r, because r is a scalar under the action of the commutation rules, just like a Casimir operator is. It is another type of vector invariant under O3. So if we know the 3 coordinates, then we'll know r, theta, and phi. And we have an r here and we have an r here. These are actually 2 different r's. One might be an r prime. And that action of this r onto this r simply gives us a delta function of r minus r prime. The procedure we're using here is very general, and I want to emphasize it. We are going to let these values act in such a way that we take a raising operator like E plus, or in our particular case J plus, or equivalently L plus, and we're going to let it act on a maximum eigenvalue. This is the simplest way to do it. So we'll let J plus act on an Lm, which tries to raise this m from the maximum value, and of course that would be the value where m is equal to L. And when it tries to raise it, we'll get a 0 if m is equal to L here. We can also re-express J plus as it acts backwards onto the r, theta, and phi, because we know how J plus, if it's an orbital angular momentum operator, can be written in terms of position and momenta. And of course that's the key. This abstract algebra must have a way that we can rewrite it in terms of position and momenta. So we let this J plus act backward on theta and phi, which will give us a differential equation to be solved. Then we'll use this J minus on this function to find all other functions and the relative normalizations by performing that LORD. We will then follow this procedure, and to do that we'll need the orbital angular momenta J's, or I should say actually the L's here, expressed in terms of spherical coordinates. Now I emphasize again that what we're doing is very interesting from the following point of view. The orbital angular momenta being expressed symmetrically in terms of x and p, that orbital angular momenta in a certain sense is an operator that lives halfway in between the position space and the momentum space. That vector, that angular momentum vector, therefore has eigenvalues that are equally dependent upon position and momentum. In order to understand what those eigenvalues, quote, look like, we project them back onto our position space because, like with a harmonic oscillator, we don't have our intuition built on eigenvalues in angular momentum space or linear momentum space or harmonic oscillator energy space. Our world, from the time we're born, is built up of looking at things in space and time. Therefore, to a certain extent, we only really understand things when we're able to take these other vectors and re-express them in terms of functions that are functions that have a distribution in terms of our ordinary space-time intuition. And that is a rather deep concept because what we're trying to do is visualize these functions in a space where we have our intuition. And this procedure that we have discussed right here is the procedure that we will always use when we can. Now, if we have a Lie algebra that has no expression in terms of x and p, or in particular in terms of x and its commutators of things that we know with x, then we are not going to be able to re-express it in terms of position space, and we will not have an intuition associated with it. A perfect example of that is electrical charge, or charm. We continue looking at the Lie algebra for the orthogonal group in 3 dimensions. And we begin with the fact that the p operator acting backwards on the position eigenstate is minus IH bar partial with respect to y times y. And that's true for all 3 components, P1, P2, and P3 with respect to y1, y2, and y3. Now we know how our orbital angular momentum is defined in terms of x and p. Now that is not true of the total angular momentum, nor is it true of spin. It's only true of the orbital part. So the orbital part has this definition in terms of cyclic ij and k. And it is a standard bit of work that we do in converting to spherical harmonics that's done in many of the standard texts on mathematical physics, where we can rewrite our LZ in terms of the spherical variables r, theta, and phi in the following ways. One can show that LZ is equal to minus I times partial with respect to phi, and that L plus or minus is E plus or minus I phi times plus or minus partial with respect to theta plus I cotangent theta times partial with respect to phi. One can find this conversion of L plus and minus from this back through the differential equations and re-expressed in terms of spherical harmonics in several standard books in quantum mechanics and in other areas where you are deriving the expressions for spherical harmonics. Likewise, L squared, Lx squared plus Ly squared plus Lz squared, can be written in the following form as a differential form in the spherical harmonics when acting on r, theta, and phi. We'll notice that L squared, L plus or minus, and Lz, none of these, when acting backwards onto r, theta, and phi, depend upon the value of r. That, of course, is because r is invariant with respect to Lx, Ly, and Lz transformations. It's invariant under rotations. And therefore, these differential forms could not depend upon r, but only upon the changes in theta and phi. We now define, as we've done before, the z component, the eigenvalue of the z component of orbital angular momenta to be m, and the eigenvalue L to be the eigenvalue, actually with L times L plus 1, for the eigenvalue of L squared. So this will be our state, L and M, that's our eigenstate of angular momentum. What we wish to find, and this is our objective here, is to find the projection of L and M onto theta and phi. More precisely, with that as an abbreviation, we want to define the projection of R, L, and M onto R, theta, and phi. And that will give us an expression of how these spherical harmonic functions are spread out over the angles theta and phi in a spherical coordinate system. We do that, as we described in the last session, by taking L plus and acting upon a state that is already maximal. Now, M cannot be raised anymore, and this is a raising operator. So when L plus acts upon L with an M value of L, we have to get 0. The reason that we form this particular differential equation is it's the simplest one to follow. And it's exactly like we did with the harmonic oscillator. We chose a minimal state there and lowered it because there is no maximum energy state for the harmonic oscillator. So we chose the bottom state and lowered it. Here we choose an upper maximal state and try to raise it. And when we do that, we can act to the right and we get 0. And when we act to the left, when we act to the right, we get L times that state. And when we act to the left with LZ, we get the expression for LZ. And we can re-express these two equations by taking the right-hand sides here and the right-hand side here and writing the term FLL of theta and phi as the definition of the projection of the vector LL, in other words where M has the value L, back onto theta and phi. And we just call it this function because it's a little bit easier to think of a function, and that's what this thing is. It's just a number that has it's dependent upon 4 values. These 2 integers and these 2 real numbers. And so we call that FLL of theta and phi. Using this equation here, when the L plus acts backwards, we know that we get this term right here times that. So we take that differential equation and write it as acting on the FLL, and we will get 0. And for this term right here, we know that LZ, from this equation here, is minus I partial with respect to phi, which we have here, and that will give times that same function, L. So now we have these 2 differential equations, and we need to solve these 2 simultaneous differential equations. And when we solve these equations, we will obtain this function, FLL of theta and phi. Let me quickly review that. We have looked at a textbook and found a reference where we can re-express the angular momentum vectors, which are the differential forms, back in terms of spherical harmonics, because we're going to let these operators act backwards, not on y1, y2, and y3 in Cartesian coordinates, but equivalently on r theta and phi expressed in spherical coordinates. And I want to emphasize that if we know these in Cartesian, we know these in spherical. So it is the same basis. It's just re-expressed in terms of another set of variables. And we have found that the L plus or minus is this differential form, L squared is this differential form, and LZ is this differential form when acting upon that vector in spherical coordinates. We then formed these 2 differential equations. We tried to raise the L, the M is equal to L value. We got these 2 equations here. We converted these into a differential pair of coupled differential equations, and we're trying to solve for this function right here, which is the projection of LL back onto theta and phi. Proceeding with our work on the O3 spherical harmonics, we're going to assume that we can perform a separation of the variables, and we're going to write FLL of theta phi as a function of theta and L and another function of phi with a parameter alpha. And when we do that, we're going to substitute that in to the equation which is the LZ equation, minus I partial with respect to phi times this function is equal to L times the function back again. Actually, we could have kind of guessed that, the derivative of something, and I'll refer back to that last equation that we had. Here we had the derivative of a function is a constant times the function back again. That's almost obvious to anyone who's looked at differential equations, that this can have a separation of a variable, phi, which in fact is going to be an exponential. So we perform that separation, we rewrite it in this form, and we're able to derive immediately that since the derivative of this is going to give us alpha, it must give us I times L. Alpha must be equal to I times L, because as we take the derivative of this, we get an alpha down, so minus I alpha is equal to L, or alpha is equal to IL. So now we know what alpha is, and we can write the function as IL phi times f sub L of theta, continuing our attempt to solve these pairs of equations. We've solved the first one of the equations by separation of variables. We're now left to the second of these variables. Here, the derivative is both with respect to theta and phi. That's why we solve it second. The other equation depended only upon the variable phi. We now see that we have our equation takes the form of e to the plus or minus I phi times this differential operator acting here, and that can be shown to be equivalent to just partial with respect to theta minus L cotangent theta. And we do that because this partial with respect to phi acting upon this phi over here brings down a factor of IL, which times this I gives us a minus L. That, when acting upon our function of theta, must give 0. And the reason is we can take these two phases then at that point and divide through by them and remove them from the equation. So we're left with a rather simple equation. The derivative minus L cotangent theta of a function is equal to 0. And one can very quickly verify that this has the solution. F of L of theta is equal to the sine to the nth power of theta as a solution. And one simply substitutes that in, verifies that it is a solution, and then one finds that FLL of theta and phi is sine to the nth power of theta e to the IL phi. Well, this gives us our important result from what we were looking at before, namely how to project the LL value back upon theta and phi as this function. So now we have found this function, which gives us our correct function for maximum m, which has the value L, but not for the other values of m, which we will now seek. And we do that in the following way. We have this function here of FLL. We know that the other functions, Lm, can be obtained by acting with a lowering operator to lower this value L down to a value m. And that must occur by acting with this lowering operator L minus m times. Now how can we figure this thing out? How did this arrive? This square root term can be derived from iterating the norm of L minus. You remember that the norm of L minus is the square root of L times L plus 1 minus m times m minus 1. And we can iterate that L minus m times and get this term right here, which has the factorials in it with just a little bit of work. When we do that, we can take this term outside of the expression, and we're left with L minus in the form of this differential operator right here. When L minus acts to the first power, it looks like this right here when it acts backward onto a position eigenstate. Therefore, when it acts many times, it will be the powers of that action of this form right here. Now this L minus operator, acting backward on the y, which we have expressed this way, can be shown to be equivalent to, and I referred to the appendix of Messiah's book on quantum theory, the same as minus L acting backwards in this form here. And of course, when y comes forward to hit Lm, we'll have that function of theta that we had before. And we end up with, there's a similar expression for both L minus and for L plus, and this is e to the I times m minus 1 phi, sine of 1 minus m of theta, d by d cosine theta, where we're taking the derivative with respect to cosine theta, of sine of plus m of theta, times our function of theta. This then allows us to have repeated actions of the L minus to a power which we call S here, times e to the im phi times f of theta. And when we have that, we can show that the powers of the expression that we had last time go to this form right here when we take, this is the form L minus, simply taken to the power S. And that's straightforward. Now, using this form of L minus to the power S to act upon our spherical harmonic, which we previously called our function, FLL of theta phi, we can write that as some coefficient, say C sub L times sine to the L of theta e to the L times phi, in order to get our YLM, our spherical harmonic, is equal to some coefficient times this expression which we've had before, e to the im phi, sine of the minus L to minus m of theta, times the derivative to the power that we need, times the sine of 2L to 2L of theta. These are the projections we've been seeking, and they are called the spherical harmonics, the YLMs are. And we have a normalization that one can show that we must have, which is 4 pi to the minus 1/2 times the square root of 2L plus 1 factorial over 2 to the L times L factorial. If we look at the lowest examples of the spherical harmonics, we can show that y00 is the constant 1 over the square root of 4 pi. y10 would be the value here, y20 the value here, y11 this value, y21 this value, and there are plots and graphical expressions of each of the spherical harmonics that are found in many of books. The extensive properties of the spherical harmonics will be explored in separate lectures. But this completes our determination to find the projections of the spherical, the states which are eigenfunctions of the angular momenta projected back up onto the position.